Hello, welcome back to Fat Mama Physics. Alrighty, escape velocity. I love this topic. In fact, one of my parodies is on this for Defying Gravity from the movie Wicked. If you haven't seen it, I haven't seen the second part. I need to watch it. Featuring, we have, of course, the final season of this entire topic. D1 episode is escape velocities. Everything is building up to this. So you have our mascots. This is Shen, who is our singer, which some of my parody videos feature. And Lulu Pig, big fan of Shen's work and singing. So escape velocity. Escape velocity, we actually use this concept a lot in space. When we talk about one cool one that will be featured in an example later is when light cannot escape from a black hole. So we talk about Schwarzschild Radius, event horizon, where that is in respect to the speed of light. We also talk about it in terms of needing to fire rockets up into space, and of course into probes into out there universe, their Voyager 1 and 2 to do their missions. And so we use escape velocity quite a bit. So then the question is, what is escape velocity? Escape velocity, think of it as the minimum amount of velocity needed for an object to escape from the gravitational influence of the body that is trying to leave. And the reason why it's the minimum is who wants to spend more energy than it's needed, right? So we often refer to the minimum amount. Of course, if you have more than a minimum amount, you're of course going to escape. But we want to ensure that it does escape. So that's why the minimum. And so we're going to use our lovely mascots for this analogy here. In this entire season, I've been using Shen as the highest gravitational pull of attraction because his singing is amazing and we love him for it. So I've often used him as the larger mass, the point mass, and Lulu Pig as the fan is the test mass. So let's have here as being some, as you can see, some distance away from Shen, and then we'll use all the way back here as infinity and beyond. Infinity and beyond. Okay. I mean, we could send Shen, or we can find the escape velocity of Shen as well, which technically is lower, but also more energy required. But just to, for the sake of the examples and the consistency of examples in the previous videos, for the consistency of the videos, we will send Lulu Pig off to infinity with some escape velocity. The funny thing is, Shen's fans will take a plane ride to all of his concerts in other parts of the world, like in the UK, or from China to UK to the States and whatnot, Australia. There's like no way to get a ticket. So if you do get a ticket to any of his concerts, I'll buy it off you at twice the price. So Lulu Pig is making space for Shen's other fans to be able to enjoy his concert in his presence. So Lulu Pig will get fired off into infinity and beyond. So to analyze, to figure out the escape velocity, which you could get from your data booklet and plug and chug, but it is important that you understand where it comes from and why it is. So to do that, we need to consider this from an energetics perspective. So conservation of energy. What that means is for Lulu Pig to be able to escape from Shen's gravitational pull, Lulu Pig needs to have enough kinetic energy to overcome that gravitational potential energy before Lulu Pig escapes off into infinity. So that kinetic energy gets converted into gravitational potential. So what we're going to do is we're going to compare the before and after, or the initial and the final. So initially, Lulu Pig's kinetic energy is unknown because it's tied to the escape velocity, but we do know the gravitational potential energy, and that has to do with the distance of separation between their center of masses, so we should know what that initial gravitational potential energy is. We also know at infinity that the gravitational potential energy there is also it is zero, because that's what our reference point. Then what about kinetic energy? at infinity, final kinetic energy. Lulu Pig could have kinetic, could be moving at infinity and have kinetic energy at infinity. But that just means that someone would need to have fired Lulu Pig off with more kinetic energy than necessary, or greater than the minimum associated with greater than the minimum escape than the escape velocity required to get Lulu Pig to still have kinetic energy at infinity. And there might not be energy. I mean, we already have issues launching things into outer space, so who's going to have the extra energy to launch any rocket or Lulu Pig off with extra energy to have at infinity? So we just go with the bare minimum. So as long as Lulu Pig is at infinity, it is not necessary for Lulu Pig to have any kinetic energy at infinity. And by definition of escape velocity, it means the minimum required amount. So at infinity, Lulu Pig's going to have 0 kinetic energy and 0 gravitational potential energy. So now we have all 4 pieces of the puzzle to put it back into our conservation of energy equation. So here I just have a picture to go over again what we in the demo here. So at distance r initial away from Shenzhen, Lulu Pig is going to have kinetic energy that is associated with the escape velocity squared. And the potential energy here is going to depend on their masses, of course. I'm using big mass for Shenzhen and small mass for Lulu Pig. And we have distance of r initial away from their center of masses. So that can be figured out. At infinity, we just said that kinetic energy can be, well, we're talking about the minimum required amount to fire Lulu Pig off. So final kinetic energy here is at 0 at infinity. You don't need any more. It's, fully escaped from the gravitational field. And then you have the gravitational potential, which by definition is already 0 because we are at the reference point at infinity of 0 joules. And another way to just think about this is if RF goes to infinity, making the denominator really big, the whole fraction itself becomes very small. So this is why gravitational potential becomes 0 at infinity. So conservation of energy by definition for mechanical energy is this. I know it's a little different than the form that we're used to. The form we're used to, it looks like this, where your final or your initial energies are equal to your final mechanical energies summed up together. And really, if you take this equation, it's pretty much the same thing as this, but I know we're more used to this one, so I will just go with this. And if we put everything all here together, we have the initial potential energy of negative big G, big M, Shenzhen's mass, Lulu Pig's mass, divided by R initial. And the initial kinetic energy we know is based off of the escape velocity of Lulu Pig, small m v escape velocity squared. And this is all equal to, hey, all the final kinetic and potential energies are 0, just by definition, as we talked about before. So we have 0 joules plus 0 joules. Basically, there is nothing on the other side. So if we take this entire equation and rearrange it, so what that means is I'm going to take one of these items and move it off to the other side using some basic algebra, then we end up with, and it doesn't matter which one, minus big G, big M, small m over Ri, is equal to negative, because I moved that to the other side, 1/2 mv escape squared. All the negative signs cancel. Okay, and hey, there are other things that cancel too, including Lulu Pig's mass. Ultimately, now we're just going to solve for escape speed. So using some basic algebra, multiplying both sides by 2 just to get rid of the 1/2. So then we get 2 times big G, big M over Ri. This is equal to escape velocity squared, and ultimately then taking the square root of both sides, canceling out that square, and arriving at our final equation for escape velocity, with this 2 big G big M over initial R, initial radius, distance from their center of masses. And one of the interesting things about this is, notice there is a 2 and in front of the GM over I, and comparing that with V orbit. Because V orbit looks very similar. Also big G big M over R. And notice, and you can think about, hey, escape velocity is larger than V orbit. It takes way more energy, speed to get out of the gravitational influence than to stay within it. So instead of just, take things for granted, look at the connections between your equations to look at their relative values and sizes to make more sense of the entire equation itself. And another interesting thing, again, similar to V orbit, is that the escape velocity is independent of the object's mass, technically the test mass. So essentially that's your small m, okay, not big M. And these two equations are, this example below is just taking what we just did and just throwing some numbers at you. It is not very hard at all. It's all pretty much plug and chug. So I'll do this very quickly. At what speed do you need to throw a 1 kilogram rock in order for it to leave the Earth's gravitational pull? So this is really just using the equation for face value. Assuming you get access to all of these values, and so you have the gravitational constant, okay, and your mass of the Earth, which you may or may not have memorized it already. In order to agree, so this question I should have been better worded. Should say from the surface of the Earth. We have a radius, so we use a radius of the Earth for the R value, 6.38 times 10 to the power of 6 meters. After you put it into the calculator, you should get something along the lines of 1181 meters per second, and rounding it up to 2 sig figs, 123 meters per second. And now, how much energy is needed to launch this rock in order for escape? So that is just the kinetic energy required. Because if you fire off a rocket into outer space, you need to, its escape velocity is tied to its kinetic energy. So the amount of work you put in is the amount of energy needed. So your EK is 1/2 NV escape squared, 1/2, and we have a 1 kilogram rocket with which is very light. So this doesn't affect our equation as much. 11181 ... with all the suffix included, and that should give you, okay, and I get 6.25 times 10 to the power of 7 joules, which is the key. Yay! Okay, so that's it. That's pretty much what this video needs to cover. In the next video following will be more elaborate examples of different ways how escape velocity is applied. And that concludes our video on escape velocity, while Joshin has more space to attract more fans, and Lulu Pig is off in infinity munching on other debris, asteroids, planets, and stars, and accumulating more mass. Otherwise, Fan Mama Physics signing out.